Hi, my name's Tom Falkenberry, and I'm an associate professor in the Department of Psychological Sciences at Tarleton State University. Today I'm going to be talking about gamma function approximations for computing closed-form Bayes factors. Now, to begin with some background, a common goal in applied settings is to compare means from treatment groups. This happens in a lot of different fields. And the main way that we do this is we perform a hypothesis test. So we are comparing competing models of some observed data Y. So the typical way to set up a hypothesis test is to set a null hypothesis, H0, where some population mean mu1 is equal to a population mean mu2. That means there's no difference between the two population means. And then the alternative hypothesis, H1, is that they're not equal. Now, of course, the question then is, how do we do this comparison? How do we decide which model best fits the observed data? And one way to do this, and this is the one that I work in the most, is to use a Bayesian model comparison. In particular, we compute something called a Bayes factor. The original term Bayes factor goes back even further, but it was popularized by Cass and Raftery in the mid-90s. And by definition, a Bayes factor for model 1 over model 0, so the subscript here 1, 0, simply indicates the preference of the models, is the marginal likelihood of the data given the alternative hypothesis over the marginal likelihood of the data given the null hypothesis. So in words, what this Bayes factor is it's the probability of observing the data under one hypothesis compared to the probability of observing that data under the other. It's a measure of relative model adequacy. Now, of course, there's a problem with Bayes factors, and that is while they are conceptually simple, just a little bit of work and we can describe Bayes factors all day long, actually computing the Bayes factors is really difficult. And I want to walk you through why that's the case. While it looks like a simple probability statement, that is what's called a marginal likelihood. So really what you have to do is you have to integrate the likelihood function over the entire range of possible parameters under the specific hypothesis. And so what that immediately introduces is a couple of technical difficulties that we have to account for. Those difficulties are, one, that we must assign a prior distribution to our model parameter theta. And because of this, the marginal likelihood expression usually involves some integral representation. So of course, those of you who do Bayesian work know that many times we get around this notion of integral representation by doing approximation techniques, particularly MCMC methods, finding ways like Gaussian quadrature. It all comes down to you need to approximate that integral. Now, it turns out with some default choices of this prior, you can actually make things even simpler than that, and that's what I want to explore today. Namely, there's a solution that goes back originally to Wang and Lau in 2016, and initially was due to them, but it came back again in a recent paper of mine, and that's with a specific choice of prior, namely the Pearson Type 6 distribution. You can read my latest paper or Wang and Liu to see this. The Bayes factor really reduces to a nice analytic representation. That is, it gets rid of the integral, and it looks something like this. What is this? Well, this is nothing more than depending on two things, namely the t-score, so if you did a t-test on those two means, and the degrees of freedom nu. And so that's really the only thing that goes into this formula. Okay, so easy enough, right? This is something I can give my students and say, here, compute the Bayes factor. We don't even really need anything more than a scientific calculator. But there's one, again, difficulty that persists, and it's that gamma function right there. Without having a programming library or a really fancy calculator, actually computing a gamma function is non-trivial. Now, of course, a gamma function is simply a generalization of the factorial. So for certain choices of degrees of freedom, you get whole numbers, and then the gamma function is a whole number. But you can see that there's a difference of a half in these two. So if you have a whole number in one, you won't in the other. And so at some point, you're going to have to get rid of this gamma function or approximate it. So that led me to the question, could we get rid of our reliance on this gamma function? So that is, can we make an approximation of that part that contains the gamma function, this gamma of nu over 2 divided by gamma of nu plus 1 over 2. So we're going to call that C nu, and we're going to see if we can approximate it. And it turns out that this problem of approximating quotients of gamma functions, it's had some interest since the 1940s and possibly even before. If you want to read a little bit of the history on this, you can see the excellent paper in the American Mathematical Monthly by Borwein and Corliss, where they present a really big survey of just papers in the monthly that talk about the gamma function and even more specifically quotients of gamma functions. So this little interesting problem pops up in some most unexpected places. So let's see if we can use it to approximate Bayes factors. Okay. So what I'm going to do today is I'm going to describe three approaches to doing this approximation. The first is we're going to use Stirling's formula for the gamma function. The second is we'll use a classical asymptotic formula that's due to Wendell in 1948. And then finally we'll look at 1 year later an improved approximation due to Frame in 1949. Again, all of these papers are referenced in that Borwein and Corliss paper. So it was really kind of a fun exploration for me to go and work out the details here. So let's look first at an approximation due to Stirling's formula. So you can read about Stirling's formula in a lot of places. It's typically used to approximate factorials, but given that the gamma function is a continuous extension of a factorial, it naturally admits an approximation similar to the factorial function. Thus, we get Stirling's formula for the gamma, and it looks like this. Well, if we put those gamma function bits from the Bayes factor in, we can get something that looks like this. It's a big quotient of a bunch of stuff. Now I'm going to spare you the details right now, but if you do just a little bit of work, it turns out that this coefficient C nu that involves the gamma functions in our Bayes factor really is nothing more than just this square root that involves the degrees of freedom nu. Okay, so we can put that in to the Bayes factor formula, and all it would require then is just a scientific calculator, nothing any more than that. So as I'm going to call this a closed form approximation. So that's one. Let's look at another one. Let's look at Wendell's approximation. This one's a little more classical even than Wendell. Wendell did write a bit more about this. You can get to this inequality in various ways. Typically, Holder's inequality gets you this, but this is a nice little bound on the quotient of two gamma functions. Now, one of the things you can do with this is if you let x go to infinity, then this part on the left approaches 1, and thus this quotient is sandwiched in between, and that tells us that that quotient approaches 1. And so now with a little bit of trickery and rearrangement, we get something like this. We're getting something now closer to the quotient of gamma functions in our Bayes factor. And in fact, if we specifically let a equal to 1/2 and we let x equal to nu over 2, we get, turns out, a very simple approximation where C nu is nothing more than the square root of 2 over nu. That's really nice. I like this one. So that's what I'm going to call the frame, or sorry, not the frame, the Wendell 1948 approximation. We'll come back to it in just a second. The third one that I wanted to mention was Frame's improved approximation. Now, why is it improved? Well, you need to go back and read Frame's paper to see this, but it's an elegant little paper. It looks like this. If you have a quotient of two gamma functions in this really cool form, it turns out to be approximately that business. Okay, so what does that have to do with our specific application here? Well, it turns out that it's simple to show that if you choose u equal to -1/2 and n equal to 2 nu minus 1 over 4, obviously, right? You can actually then transform this left-hand side into C nu, that quotient of gamma functions involved in our Bayes factor. And so if we work from there, we use this Frame approximation, C nu then is approximately equal to that little thing right there. And again, if we put in u equals -1/2 and n equals this, then, well, it looks like that. It looks like it's a bit more complicated now, but do a little bit of arithmetic on it, and we get it down to 8 over 2 nu squared minus 2 nu plus 1, all to the 1/4 power. So the common thread that all of these approximations have is they're all closed form. They're all things that I can compute with a simple scientific calculator. They do not require being able to approximate the gamma, or to compute the gamma function at all. So you might ask, well, these are all approximations, right? They're not exact solutions. How good are they at approximating? So to investigate that, I ran a little simulation study. And so for sample sizes of 4 up to 100, I generated 1,000 random data sets each, computed the analytic Bayes factor, and then computed these closed form approximations and plotted the percent error as a function of that sample size. And here's what we get. We get, of course, that the percent error goes down as sample size goes up, but remarkably, these two down here, these are the Stirling formula with the little short dashes, and then the long dashes is the frame approximation. They do extremely well. Even with sample sizes as low as 4, the minimum, the percent error is less than 0.5%. So the frame approximation's really good. The Stirling formula approximation gets good really fast. Once you get up to n equals 20 or 30, there's virtually no difference. The Wendell approximation is actually okay, but compared to these two, I mean, it's not any good. But again, keep in mind the absolute error, the percent error that we're dealing with here is 1% at the most. So these are really good approximations. So in summary, we can compute these Bayes factors in closed form. In other words, we can get rid of the gamma function by approximating the gamma function component as in one of 3 ways. We can do it this way, which is Stirling's formula, and as we saw, it's a pretty good approximation. We can do it this way, which is even simpler. This is Wendell's approximation, but it's not quite as good. Or then finally, we can do it this way, which is certainly the most complex, I think, of the 3, and it is the best. So we'll see how it works in applied settings with my students who are doing t-tests on independent groups. But that's all for this talk. If you have more questions, please do contact me. My contact info is there on the screen, and look forward to visiting with you about computing Bayes factors and approximating gamma functions to do that. Thanks so much.